Hello, welcome back. Today I would like us to revisit feminist science and consider the work of a feminist theorist, Professor Karen Barad, an American gender studies professor known particularly for her theory of agential realism. She is currently a professor of feminist studies and philosophy at the University of California. Her publications include such masterpieces as Meeting the Universe Halfway and What is the Measure of Nothingness. Barad can be described as a leading light within the feminist science community and is often cited in feminist publications and papers. Her books and essays are often required reading in gender studies courses. Barad presents us with a particular problem, in that she is a qualified physicist and her work often references quantum mechanics, a field that is often counterintuitive and complex, and therein lay the first potential problem. There is also another equally difficult issue to address hidden within her work, and that issue is less obvious. It is this less obvious issue which will be the focus of this video. So, what is the best way to approach this topic? Well, what we shall do is approach it back to front. That sounds an odd way to approach anything, I know, but bear with me because what we shall do first is look at the consequences of her work, and then we will examine her work to see if we can determine the origin from which these consequences flow. And by approaching it this way, I hope that you will understand the basis of my criticisms of Barad's work. Before we start, it would be extremely useful to hold one concept in mind. The reason we need to keep this particular concept fresh in our minds will, I hope, become obvious as we venture into the surreal realm of feminist quantum theory, and I can think of no better explainer of what it is than Professor Carroll.
If you have a tiny bit of physics education, you may have come up against the question, is light, for example, a particle or a wave? A wave is sort of a vibration in a field. So what is more important? Is it the particle aspect of reality or is it the field aspect of reality? It's fields. That's the answer. It's not a mystery. They always tell you that question. They never tell you the answer. I went decades of my life. So what's the answer to this? This is the answer. It's fields. Any questions about that? So I'm going to go into a little bit more detail, but not too much. But this is the crucial slide, okay? There's no more information. There's nothing more to come on this slide. The reason why the Higgs boson as a concept is hard to grasp is because you need to stop thinking of the world in terms of particles. You need to start thinking of it in terms of fields. And you say to yourself, well, but things like this table are made of atoms, and atoms have electrons and so forth in them, and the electrons are particles, right? There are particles in the world. No, there aren't. That's the secret that we physicists have never told you, but here I am, I'm going to tell you right now. The reason why you're allowed to think of particles is because of quantum mechanics. The world is made of fields, but quantum mechanics says when you look at the world, you don't see it directly. What really exists, according to quantum mechanics, is immensely richer than the things we can actually observe. So the reason you think that there are particles is because there are actually all these fields filling empty space. At every point in space, there's dozens of little vibrating fields in front of you. But quantum mechanics says that when you look at the fields closely enough, they resolve into individual particles. So on the picture on the right here is from David Deutsch, an Oxford physicist, one of the founders of quantum computation theory. And he says, imagine you are a frog. He doesn't care whether you're a frog or not, but frogs, it turns out, have slightly better vision than human beings do. And what that means is that frogs can see individual particles of light, photons. You're all seeing light from the light bulbs here, from the screen, and so forth. Light is two things, right? Light is a wave in the electromagnetic field. So there's a field filling space. At every point here, there's a little electric field, a little magnetic field. They're vibrating, and that's the light that is coming to you. But quantum mechanics says you look at that light very carefully, and it turns into individual particles called photons. Photons are the particles that you see when you look at a wave in the electromagnetic field.
So, if we are to believe Carroll, it's all fields, and he expressed this with both precision and certainty. The reason why that is an important concept to keep in mind will, I hope, become obvious in a little while. Think of Carroll's explanations as an intellectual life raft thrown to us as we struggle in a sea of quantum nonsense. Don't worry too much about the science itself. Barada's understanding of quantum mechanics will not be our primary focus, although I might indicate some questionable assertions along the way. Sean Carroll has already provided us with all the quantum physics we need to begin our adventure. Before we go on to the next video clip, I think it's best if I explained what is supposed to be happening. What we will witness is a close reading of an essay by Professor Barad, which took place at Leeds University in 2014. Now, what I understand by the term close reading is that close reading is the careful, almost forensic analysis of text in order to isolate any arguments contained within, which would then allow the reader to determine the form and validity of those arguments. This is a concept that would be familiar to anyone who has done philosophy. What we are about to witness is described as a close reading, but in my opinion it seems more of an exploration or a futile attempt at comprehension. But let's drop in and listen to the discussion of Barad's essay and listen as professor and students struggle to comprehend her use of the term intra-action.
Stories. So she uses her word, it's her word, intra-acting. Although she refers to it as somebody else's, so she's the person who popularized it, let's say. There's maybe a footnote in one of her earlier books that explains the source of the word interacting, which I associate with her. These
can we just explain it?
We did, yes. Well, yesterday I mentioned it when in the lecture. To interact means that you presuppose there are two entities which come into contact, and they interact, and then they produce something which is a third thing from that interaction. Interaction means that there is nothing, and then the two entities that are interacting come into existence through their interacting. So matter actually doesn't, so there isn't space and time and they interact, or there isn't an electron and another thing that exist and then they interact. To see physics as a situation of entanglements where the two entities come into being in the moment that they're interacting. For example, if you take a photon and you throw it through a slit and you split it into two photons, these two photons didn't exist before, and they are entangled because when you split a photon in two with a the traditional quantum physics way of entangling photons is you split one, and then the two somehow have a memory of each other, and they are forever entangled. So if one photon does this, the other photon does that. And then this one does this, and this one does that. This is the basis of future so-called quantum communications that will be based on the fact that you do not send any message. There is no information, but the elements in the two distant points are entangled. Oh, I don't know if it's related to time travel, but it's certainly related to the physical world that we live in, which is a world of entangled beings and interactively generating themselves. And it's very visible on the small level. Now they're in physics labs trying to entangle big things like atoms. But to do that, you have to freeze them and make them very cold so that you can actually do that with an atom. But it's proven in a laboratory only on smaller elements that they're entangled through their coming into the world. And the way that you disentangle is one of the two has to be entangled with another, has to be then itself entangled with something else. So in a strange way, the stories that we are telling each other are partly binary. I mean, entanglement occurs between two, not three, but then they're constantly re-entangling themselves. So it's a multiplicity, but it's interesting if one has to rethink the question of the binary for a moment. And one of the notebooks that investigated that question in an incredibly rich way was the anthropologist Eduardo Viveiros de Castro, speaking about binary and early structuralism and Lévi-Strauss, and maybe second institute I could put that notebook on the reading. But to go back to this, interaction is that. It's the fact that we come into the world, we're not, two things or more things are not there, and then they're there together, and they're there in the moment of an interaction. They cannot come into the world alone. That's the basic of interaction.
Now, I can imagine all the physicists out there chewing on their mouse mats at this point, but I'm pretty confident that most viewers, even if they're not physicists, will be harbouring the suspicion that what they had heard in this session was utter nonsense. And indeed it was, from beginning to end. I won't labour the point and detail every misconception, but there is a major flaw in reasoning that needs to be corrected before we move on, and that is, you don't get 2 photons for the price of 1. Remember the explanation by Carroll in the last video clip, when he described wave and particle duality. The classic double-slit experiment demonstrates this wave-particle duality, not entanglement. It shows that a particle can interfere with itself, thus demonstrating that it really acts as a wave in some instances, but can be observed as a particle under different circumstances. Whichever way you look at it, when considering the basic double-slit experiment, we are only dealing with a single entity. The wave passes through both slits in the double-slit experiment. When we try and observe one slit, that will collapse the wave function, and we see a single photon. We don't get 2 photons. We get a single photon, and quantum entanglement requires more than a single particle. So both the lecturer and students in the session we watched were struggling with the fundamentals, but that's not our concern. Quantum mechanics is counterintuitive. It involves complex concepts that don't lend themselves to common sense. So it's not surprising that people struggle or even get things wrong. What should concern us, though, is that the confusion we witnessed during the session at Leeds University is primarily driven by an essay penned by a qualified physicist. So let's now turn to Barad herself and listen to a few sections of a keynote speech she delivered at a 2014 Feminist Theory workshop, which took place at Duke University.
Mode, so that you can not only see how the nature-culture binary is being deconstructed through physics, but also perhaps feel it, if not in your bones, maybe by some disorienting proprioceptive effects. Staying with physics for me is what my friend Donna Haraway calls staying with the trouble. My political commitment is in my work is to questions of science and justice, and part of that work is deconstructing the science in a Derridian sense, showing ways in which physics, indeed nature, deconstructs itself. This does not mark the downfall of science, of course, but it does enable political possibilities for reworking its unquestioned authority in a way that is epistemologically robust. That is, its radical openness, its indeterminacy as a practice, its ongoing questioning of itself is about the work of reconfiguring science in relation to justice.
Barad, like all feminist scholars, views her science through a political lens. She presents as an almost textbook example of a Lysenkoist. She references her commitment to the project of deconstructing science. This suggests she has embraced postmodernism. She refers several times to the work of Derrida and explicitly uses the expression in the Derridian sense to qualify some of her more poetic statements. This is a problem, because while I can see the attraction of continental philosophy for someone in the humanities who might find form more aesthetically pleasing than truth, it is a philosophical position that is difficult to justify in the natural sciences. Now, I'm not going to cover postmodernism or Derrida's work in this video. We simply don't have the time. But it should be noted that most of Derrida's pronouncements on science are nonsensical. Perhaps the most infamous and often quoted is his comment on relativity, where he stated with magisterial certainty that the Einsteinian constant is not a constant. I haven't the slightest idea of what this might mean, but I'm pretty sure that neither did Derrida.
A photon of a given color is emitted during a leap that is outside of time. A photon emitted before it reaches where it will have gone at an indeterminate moment after it has left in order to be just the right color. Do you want me to say that one more time? A photon emitted before it reaches where it will have gone at an indeterminate moment after it has left in order to be the right color. A color given by the size of a leap that has not yet happened. that is, as it were, suspended in an indeterminacy cross-cut by a difference that has not yet been counted. Causality run amok. A quantum leap is a discontinuous movement, and not just any discontinuous movement, but a particularly queer kind that troubles the very dichotomy between discontinuity and continuity. Indeed, quantum discontinuity troubles the very notion of dichotomy, the cutting into two itself.
Well, the good doctor was so impressed with her clever arrangement of nouns, she thought it worth repeating. It is, of course, utter bollocks. It's just noise. I think when viewing such statements, even if one is not a particle physicist, it's easy to recognize the fakeness, because we all have an intuitive sense of the constraints imposed on scientists. Even if we are not physicists ourselves, and are unable to determine which arguments are valid, we can still come to know when somebody is ignoring entirely those internal constraints that make science what it is. I defy anyone to attribute meaning to her statement as a whole. Barad invites her audience into a fantasy realm, where we are expected to commit to a joint enterprise of communal deceit, where the professor gets to play the intellectual and her audience can pretend to think, even if it's obvious they're doing no such thing. It is this type of complicit deception that has infested most of the humanities departments within the academy, and it is the source of confusion we witnessed in the earlier video. Barad, it seems, has gone full Derrida, and the product is a stream of unmitigated postmodernist drivel.
Stage left. A ghost of Thomas Young and his famous two-slit experiment, an experiment Thomas Young famously performed but probably never did. The two-slit experiment, the grand identity filter, the perfect litmus test of the character of being, the greatest ontological sorting machine of all time. Thomas Young is lecturing. Sound waves from the two speakers set up at the front of the hall form a sonic diffraction pattern so that alternately spaced conic sections of the audience can hear Young's voice with clarity, while the others sit with quizzical looks, not hearing a word, and still others have their ears plugged because the sound is so loud as to be unbearable. One of these days I'll set this up. The words come clearly to those who are well placed. This can be demonstrated using a simple instrument which I call a two-slit apparatus. It's very simple, really. It has just three parts: a device that is the source of the entity being tested, a barrier with two holes in it, and a screen placed some distance farther back. Now, if you want to know if an entity is a wave or a particle, you simply fire a bunch of them at the barrier with the two open slits. One of two patterns will appear on the screen. If most of the entities hitting the screen collect directly across from the slits, the entity in question is a particle. On the other hand, if a distinctive pattern with alternating bands of intensity appears on the screen, the entity in question is a wave. Note that the pattern of alternating bands, or diffraction pattern, is similar to the wave pattern formed by overlapping disturbances when two stones are dropped simultaneously into a pond at a small distance from one another. In summary, my device, the two-slit apparatus, gives a surefire method of distinguishing waves from particles. In this way, it is possible to characterize all of nature as belonging to one kind or another. Some audience members clap when Mr. Young has finished. Others... I know where you are in the diffraction pattern. Others have already left in frustration and asked for a refund of the ticket price. Someone notices that the remaining audience members form a pattern of bands radiating outwards from the stage. Interested in this phenomenon, one person raises her hand, but Mr. Young has already disappeared.
Thomas Young spoke on the 24th of November 1803 to the Royal Society of London, describing his historical double-slit experiment. His Royal Society talk was published in the following year's Philosophical Transactions, and that would have been in 1804. The difference between the time of his talk and its later publication is a minor point. What is not so minor, though, is Barad's description of the talk itself, which is almost entirely inaccurate. He did actually demonstrate his experiment. The slide Barad displayed in her presentation is taken from the account published in Philosophical Transactions. That graphic does not represent heavy metal stage speakers blasting the audience, but simply a graphic representing an interference pattern, blasting speakers, deafening noise and dead audio zones. This is a complete fantasy. Was Barad describing an overextended and poetic metaphor? Or perhaps it was an attempt at feminist humour? Or maybe the good doctor is a fan of steampunk fiction? Who knows? What is certain, though, is the talk was given by Thomas Young in 1803, 70 years before the first speaker was patented by Alexander Graham Bell, and 120 years before speakers capable of being used as described became available. So the entire scenario painted by Barad is a fiction, unless, of course, Thomas Young was even more of a genius than we suspected. Such schoolgirl errors hardly inspire confidence. So we come to the end of our adventure into the surreal and somewhat confusing world of feminist quantum mechanics. Barad is held in extremely high regard within the realm of feminist science. Indeed, she is often described as an eminent scholar. But when we view her work, we find that science is being distorted by a political lens, and we see a scientist who has embraced postmodernism and feminist theory. Barad is a qualified physicist. How capable a physicist, it is difficult to determine, because her work is obfuscated by a thicket of Derridian nonsense. She seems to take pleasure in wearing the cloak of intellectualism, but the philosopher Roger Scruton has presented cogent criticism of intellectualism that rests on the work of the continental schools of philosophy, which includes the work of Derrida. Barad is not an intellectual giant, but rather a postmodernist hobbit. We end our adventure at this point. I hope you found something of interest in this video. If you would like to support my channel, I now have a Patreon page. If you're unable to support my work through Patreon, then you can share, like, or comment. It's all good. Thank you for watching.